Yes, thank you for everyone, Victor and the organizers, for organizing this very nice event. As Victor said, with very nice weather and on a bank holiday, so a lot of people showed up here as well as online. So this is great commitment. So a few things. Yeah, so there are a few. I mean, there is less material than I would hope to share, but there is some stuff on this webpage, which has some of the slides are there, and then yeah, the webpage looks like this. So there's slides here, and then there is some proofs which, if I have time to cover, I will cover these. Otherwise, you can read on your own. And some of the coding demonstrations I will show, more or less, they are the same implementations as you could see here, right? So I will come back to these ones. So there's not as much as I would like to share, but it's something. So when I share code and when I show you code and implementations, you can always go back and sort of practice from there. Okay, so let's start properly. So what I will do today is to assume that basically you have no prior knowledge about filtering. Many of, not many, but some of you I recognize that you do know about filtering a lot. So this session could be sort of basic for those of you. But the goal is to sort of bring everyone up to some sort of level where we can follow the rest of the week, right? And there's a lot of advanced. There's going to be a lot of advanced lectures, and hopefully these will help you to sort of start understanding those. And sort of the outline is like this: state space models and filtering. So it's general concept of. So I will focus on filtering, not more general as sequential Monte Carlo sampling, because it's more general than just filtering problems, obviously. But I'll just focus on filtering. I'll just introduce the basic Kalman filter. I will not go into nonlinear Kalman filters that much. I will just mention and point you towards like the names of the popular algorithms in this sort of Kalman filtering domain. And then I'll go into Monte Carlo methods, which is obviously motivated by particle filters. So I hope to cover up to here, basically. I don't think I'm going to go back to background, which is obviously a typo there. So smoothing and a bit of parameter estimation is in the slides. It doesn't mean that I'll be able to cover all, but if I go all the way up to particle filter and introduce properly the particle filter, then you must be ready for the rest of the week. That is sort of the goal of today. Okay, so let's start from like basic definition of the problem. So what do we want to do, and what do we mean by state space models and filtering, basically? And I will actually in a second I will just simplify this. So now this is more complex model than I will start from an even simpler problem, but just to set the background why we will even deal with the simpler problem is we are interested in this sort of model. So what is this model? It's called a state space model or a hidden Markov model, usually. Continuous space hidden Markov models, or I mean, this could be discrete as well, but I will not consider those cases. And so this sort of model has two main objects, right? One is the process X process, and we usually call it hidden signal process or signal process, or yeah, there's a bunch of names for it. The X process is a Markov process that we will assume that is unobserved, right? Something that we don't know, something that is of interest to us. So what could that Markov process be? Is a lot of sort of interesting dynamical systems out there. It's modeled by Markov processes, right? There's a lot of applications in dynamical systems. If you want to track a vehicle in typically more like tracking applications, the Markov process could represent the state of a vehicle moving on in the space, right? Again, if you want to sort of have space-related applications, again, it could be a state of a satellite, location of a satellite, position of a satellite, and so on. It could be in finance, it could be a volatility process, right? So because in finance, what you want to do usually is to estimate the volatility from data. So volatility is usually not available to you. Volatility is just the variance of the observations. That's simplified. And you can imagine there's a lot of other scenarios where there is some sort of underlying process. You can imagine this as a you can think about it as general as you want, like maybe it's even solving a PDE or partial differential equation. It's a physical system, something that evolves over time, right? And then we have the Y's that are observations. So this is also called like a partially observed model. sometimes you will see that sort of naming. So the data we observe that depends on, so each y is conditional on x, and each y is conditionally independent of other x's given the x, right? So y1 is conditionally independent of other observations given the Markov process, underlying Markov process. So essentially, there is some hidden signal process you can't directly observe, but you can observe some signals from. In the case of tracking a car, or I mean, I always like the example of a localization, right? How Google localizes us. So sort of we have this phone here and sends a signal. Our location is not available to obviously person who wants to localize us. But what we send the base signal to the base station, right? And then let's say I am moving, X processes me, I'm moving around with my phone, and I continue to send the signal to this base station, right? And that's like Y. So Y and X are quite different. X is my location in the map or in 2D or on the Earth, depending on how you sort of formalize the positions, I guess. But Y is just some sort of power signal that goes to base station, right? Okay, the goal will be throughout this week, I guess many people will try to tell you about the problem of recovering X's from Y's. That is the problem. Of course, I am around, I send my signals to base station, and then the goal is to localize me, right? Estimate where I am and where I am moving, more importantly. Okay, so there are there are three objects, but two are the most important. So in order to mathematically formalize something like this, you have to define a transition model. So this is how I will denote the transition model. If you're not very happy with this dx, you can imagine it as a transition density. So you can imagine it as just tau xt given xt minus 1. Right, so I will typically assume all the time there's densities. I will not do anything fancy. So this sort of describes how the system evolves. So this is sort of what you know about the evolution of the system. And then there is going to be likelihood. Likelihood basically describes how each x becomes a data point, right? So for example, if it's a really simple problem, it could be just Gaussian noise. So if you are able to observe pretty much everything just with Gaussian noise, then it's just Gaussian noise centered at x. But of course, in the example of a base station I was talking about, it's a very complex likelihood, right? Typically very complex likelihood because there's a physical system in between, there's air and there's walls and all. Okay, so this can get very complex, right? So depending on how tau and g are formulated, of course, the algorithms that are used to estimate x's from y's change a lot. In the simple cases, I will start showing if tau and g are simple, then there are analytic algorithms. They are called Kalman filters. And there's variations of those filters when tau and g, again, somewhat structured and simple. And then most generally, if you want to sort of infer very like general x from y in very general settings, then we will use particle filters. Right? That's it. I'm done. So yes, so what we basically want is to estimate these x's from y's. That's the problem I was talking about. But in particular, I will focus on more particular, sort of more technical or more precise problem, is that we are typically interested in estimating expectations of this sort of posterior distribution. So I will sort of introduce these a bit, a bit more detail in a bit. I'm just now kind of warming up with just, sort of throwing you in the water for you to learn how to swim, I guess. It's just, we want to estimate the posterior of xt given all the data available, of course, and then we want to, so this is the conditional distribution of this latest state given all the past data. So I observed a bunch of data points and I want to estimate the posterior of those. And not only that, I want to compute moments potentially and expectations with respect to it, right? So what this phi could be, so why do I want to do something like this? Phi could be just an indicator function. If it's an indicator function on a set, then you're trying to estimate state of x being in a set, the probability of x being in a set. This is of interest, obviously, if you want to sort of estimate if this object is in this area or not, that kind of probability, then indicator functions are one choice. If you want to estimate mean of x, the most expected where you can find it, the first moment, second moment, the variance, all sorts of things you can construct from this. Right. So the main sort of goal would be estimating these expectations as well as potentially estimating the posterior itself, which are two different problems. Okay. Feel free to ask any questions. Is everyone I'm going slow. So, okay. So in order to introduce how the Kalman filter works, I like to introduce usually the sort of setting of sequential inference because it's an easier setting, and it gives you the idea of updating with data. Sort of makes it much easier to introduce the idea of Kalman updating, at least for me. So, for example, let's consider a simple setting where I have a system like this, right? What happened? What changed? I don't have a sequence of x's each generate y's. I just have one x that is my hidden location. So this is basically I am standing here. I want to do localization and I'm standing, right? So I'm not moving, but then I continuously send some signals. So I send these signals. And the goal here, the simpler goal, before we go to the XT situation where it's a more complicated thing to do, the idea is to estimate the conditional distribution of X given all the data, right? And there's another aspect to this. What we want to do. This is why we call it sequential inference. I want to do also to process these observations sequentially. Right? I just don't want to. I don't want to store all data all the time and update my posterior. And if data comes, I have to do it all again. I don't want to do that sort of setting. What I want to do is process YK data, estimate this, maybe expectations if I want to. Then if YK plus 1 comes available, I just want to sequentially update my posterior instead of reprocessing all the data. Right? So let's look at this problem, which is going to be sort of almost Kalman filtering without prediction, of course. So how would you obtain this sort of distribution iteratively? You can just use Bayes rule iteratively, right? So there's nothing very complex going on here. It's just Bayes rule used in a sort of clever way. So what can you do if you are given? So obviously you are given prior on x0, right? If you look at the model, I define the prior on x, not x0, prior on x, so pi 0 of x. So obviously you start from there and you just want to derive one step of the update rule. So if I can derive this update in terms of this one, obviously I can start from pi 0 of x, go to x given y1, and then continue that way, right? So how can you do this? You just write out the Bayes rule and then get an iterative rule out of it. So how does it work? You just write here the Bayes rule. This is the joint over the P of y. It's just the joint distribution over the marginal. And then you use the model relationship. Model relationship that tells you that so each yt depends on x this way, and then you can then write the joint distribution of x to yt minus 1. And you can factorize the marginal likelihood, which is called, typically this is called marginal likelihood, or the model evidence, or let's say the marginal y's in this way, because this is true for any set of variables. And then you can collect these red terms into a posterior, and then you get sort of an iterative update, right? You basically get a Bayes rule where now you can see that this is sort of a Bayes rule where G is our likelihood, and then this thing is our prior. So what I did here is that I just said, okay, there is a way to do, you start from a prior, update your first posterior, use that as a prior, update your second posterior, use that as a prior, and go on like this, right? This is how we would do it if you have a static estimation problem. That's sort of just the iterative application of the Bayes rule. Right, that's what I'm saying. So we started, so I should finish at like 10, 11, right?
At 11, we have a break.
Yeah. Okay, so well, how do we go towards sort of a tractable setting? I mean, this is sort of an abstract formula. Of course, to realize this, there's many different things you can do. Typically, Monte Carlo methods as well, but it's tricky. Of course, in this setting is kind of trickier than actually the filtering setting. You will see. One way to do this is, of course, if your model is simple and you can do this update rule analytic. So now, most of you probably have seen Bayesian stats courses, I hope, or at least maybe basic probability courses where there is a prior likelihood posterior kind of setting. All of you probably have seen that if everything is a Gaussian, we like Gaussians. If prior is a Gaussian, likelihood is a Gaussian, and there's no nonlinearity in the process where, you know, the Gaussian likelihood, let's say, doesn't have a nonlinear function in it, then we can do these things analytically. Is that a common knowledge? Or? Yeah, good. So we can do these things analytically. So that's what you would do. Can we, if you're given a model like this, okay, so just to set the notation a bit, mu0 is the prior mean and v0 is the covariance, obviously, and then ht is this, we will typically, it's usually called sometimes observation matrix. Is it? I mean, I guess it's an observation operator of X, right? So what's the meaning of it? It could actually, it is what happens to X as it becomes an observation. So H is applied to X, and then there is some noise around it. Okay, and then there is this sort of thing that you can derive. I will not derive this. But what is this? Basically, if you had one Y, so if you had a single Y, and you wanted to start from mu0 and compute the posterior of Y, mu Y and Vy, let's say, or mu1 and V1, this would be the update rule you would perform, right? So there is a lot of sort of interpretations of these terms, but I like to write it usually in one go because, okay, it's a bit of a linear algebra to derive this, but there is one step rule from a prior that is Gaussian, likelihood that is Gaussian in this form, then you can get the posterior in this form, right? One step. And then, of course, once you get it one step, so you get mu1, that is just using y1. We have seen that what we are doing in the previous step is just using this as a prior, so you can just iterate this, right? So in order to obtain, in other words, the moments of this guy, mean and the covariance of this guy, you can just iterate this sort of update rules, and that's all you do, right? That's the sequential inference rule. As you iterate these things, you will get mu and mu t and vt, which are the moments of the posterior. Sorry, the sufficient statistics of the posterior. So mu is the mean, v is the covariance. Okay. So this is a very, like, it's at the heart of the Kalman filter, obviously, because if you know Kalman filter, it does look like this, a lot like this, but there's of course a slight modification I will introduce. But this is not Kalman filter, this is sequential inference, we call it for a Gaussian model, right? This is how you would do online inference. Obviously, you can do linear regression with this. Right, in the linear regression, HT would be B transpose, and yeah, well, I guess if you want to infer, if that's a bit of a different problem, I guess you want to infer beta there, but if you want to do linear regression online, this is how you would do it. Okay. Right, so let's move from static inference to, again, what we discussed before, the dynamic inference. So the difference is, instead of a single X, we have an evolving set of X's. And then we have sort of this Y's that each correspond to a single X. And then now I want to use the idea I introduced here is obviously become a subroutine of that, because obviously I will need to update, given an X, I will need to update the posterior of X given from Y. But of course, because I have dynamics now, I don't have a static X, I have to sort of do also predictions in between, right? That is what is. Okay, so what is the, how is it done? It's basically done as, like, at least in the Kalman filtering setting, this is going to be a bit different in particle filters, but in the Kalman filtering setting, only thing that changes is, remember now, again, these are all, whenever you see these sort of dx's, you can also imagine these are x and x. Well, I guess then you imagine dxt minus 1 at the end, right? So x times dxt minus 1 at the end. These are just notation. But you can recognize the one on the right, this one, is really the one that we have just seen. Before we saw the prior, so this is sort of the prior here, was just the pi t minus 1, right? In the previous formula, we had the pi t minus 1 as the previous posterior, we had gt and pyt. Now, because I have dynamics, I can't just use previous posterior as the prior, so I am here. This is my posterior, I have it. But before I can process next observation, I have to sort of go through the Markov transition, right? Because there's dynamics. Of course, then the way to handle that is you have a prediction step. And the prediction step, exactly what it does is it takes pi t minus 1. So this is the posterior of the previous time. Again, like, I'm not writing the conditional y1 to t minus 1, but that is that distribution. I have to sort of pass it through the transition kernel. So I have to construct the predictive measure. So this is basically the predictive measure of, let me see. So this is like y t minus 1. And this is the predictive measure of xt, right? Given all the past data. And then you get the predictive measure of xt given all the past data, you plug it in here, then you do the regular update. So obviously what you need for this to be tractable, what you need is you need this part to be tractable as well, right? So if you take the Gaussian posterior of previous time, let's say we start from a Gaussian at pi 0, at pi t minus 1, it is going to be a Gaussian density, and I pass it through this transition kernel, it is, again, has a linear structure, we will see in a bit, then the hope is that this thing still end up being a Gaussian. If it ends up being a Gaussian, then using it as a prior to a Gaussian likelihood will end up being, again, analytically tractable, and you can get like just this set of rules, update rules as an algorithm, right? So this would be just set update your mean and covariance. This would be just update your mean and covariance. That's exactly what we do. So how does it work? So for example, if you want to compute the prediction, sorry for this psi and pi changing. In any case, if the letters change here, which is likely because it's a combination of a different material, you just need to look what is inside. That is xt given y1 to t minus 1. So this is predictive measure, right? So I typically use psi here, but here's the typo. Okay, so prediction, how do you do prediction? We have seen that prediction is the difference between the static case and the dynamic case. This depends on sort of the model. Of course, the formula, as I wrote, that was in very compact in the previous slide, is explicitly written this way. So you get your previous posterior distribution, and you have to integrate out to t minus 1 in order to get the marginal of xt given y1 to t minus 1. Right? This is the prediction step. In terms of densities, yes, I made it easier. You can just write it this way. So if this is sort of confusing, it is just the posterior of previous time in terms of density. So assuming that at pi 0 you have this, right? Assuming that you have this, we are just trying to do induction kind of argument. And then if you do if you integrate out xt minus 1, then you get the predicted measure. Okay. Yeah, so we have already seen the update rule. Right? So update rule is if prior was a Gaussian and the likelihood was a Gaussian, we know that the update is available to us. It is now effectively the case that our prior will now be the predictive measure instead of the previous posterior. And update will be the same. Right? So this is basically the filtering recursions, as you would call it. Usually when people say filtering recursions, they usually mean this prediction recursions in terms of distribution. So I had one sort of formula here. This was the formula for the prediction, right? Just integrate xt minus 1. And then I have the update formula here, use the predictive measure as the prior instead of the previous posterior with the likelihood, and you get your posterior of xt given y1 to t. Right? These are called filtering recursions. Okay, it's a good point to get questions here, because then I will go into specific models and so on. Everything clear or confusing?
Not technical, but where can I find the slides again?
This was
I think you all should have an email with from Sarah. Did you receive an email, some of you?
yeah, sure. If you have an email, please pass it. Okay, so let's go to specifics and say, like, if these formulas, yeah.
Can the kernels change over time? Always also like the same function, or can it change over time?
So it can change over time. Obviously, here it's very general. Anything can happen here. These are just rules. Nobody knows how to implement, I guess, for the very general cases. Typically, we will just fix G because it's easier to write formulas that way, but it can change. But you have to know. So you likely changes over time. So let's say your H changes. So I will go like here, let's say. If you likely changes over time, it means pretty much H's are changing or R's are changing. And in order to do filtering, you need to know these, which is a challenge, I guess. How to estimate those is a different problem. I'm sure there's going to be some talk of parameter estimation, but in theory, they can change.
And also how change.
Yes, tau could change. For example, here as well, this A can change over time, Q can change over time. But again, you need to know how they change it, in order to be able to do filtering. They can change. Okay, so let's go into the very famous algorithm then. Proposed in 60s. The one thing that I like in this presentation is the references, but I don't think any of these things require a reference. Just Googling will give you right papers. Kalman filter, right? What is a Kalman filter? So there's a lot of discussion about in the electrical engineering community how to interpret this, but at least I will introduce you one easy way to understand Kalman filter. So let's say we have a state space model. Remember the one that we had x's and then we had each y drawn from x's. It's given this way, right? What is this model? So there's a prior in the initial condition. That's just a Gaussian prior. And then you have a transition model that is linear function of xt minus 1. So you have some sort of linear operation. So what it could be, like I'm in space and I'm going just like in direct line, right? So I'm an object walking. If I'm not doing crazy moves, I'm just walking in a linear fashion, then you can model my location in 2D as the linear evolution of my previous time. Right? So I'm here, I'm walking in a straight line, then you can just write that equation, you can find the corresponding A. You will actually do that in an example. So it's a linear evolution model, so your system is sort of linearly evolving, and it's not such an abstract thing. I mean, it arises in plenty of physical systems where, let's say you have a linear PDE and you want to sort of infer states of this PDE, observing some parts of the state space, then you may end up with a linear equation like this, right? These A's will coming from the physical system, maybe finite elements like stiffness matrix and so on, but still it is relevant to the model. Obviously relevant given our tables. And then the likelihood is again, just as in the case we have seen for the static model, it's a linear Gaussian likelihood. So whenever you see this weak linear Gaussian case, maybe Pierre will talk about those things. Linear Gaussian means just this stuff, right? So you have a linear evolution model, linear observation model, and this is basically what everyone means when they talk about linear Gaussian model. At least that's what I hope they mean. And then, of course, the question is, can we compute the filter analytically? So to get you a bit more with the sort of notions or the language people use in this community, people usually refer to this simply as the filter, because we refer to problem as the filtering problem. And this sort of object posterior of xt given y1 to t is usually called filtering distribution or a filter in short. Okay, can we compute the filter analytics? Now, everybody sort of, I guess, knows the answer by now. Only problem, as I said, was the prediction step. Remember, I said we need to just compute this prediction, which was an integral over the tau, right? So it was the previous posterior and then the tau and xt minus 1 integrated out. And there's a simple rule and there's a simple implementation as simple as 2 lines here. So you just have formula in closed form, the prediction formula. So the prediction, so the posterior of xt given all the past data. Usually people do this mu given t given t minus 1, that kind of stuff, but it is a bit clutter, right, all of that. So I just wrote mu hat, sorry, tilde and v tilde. And these are as simply given like this. I mean, it's a kind of intuitive formula. Why? Because if you think that I'm here in expectation, so mu t minus 1 is your best estimate of where I am now, and you know how I am moving, that's the A matrix, so I'm moving in a linear fashion. Of course, you're going to guess where's this guy going, probably just going to the mean at time t without seeing my new data. Your best guess would be just multiplying your evolution model and then your previous mean. Of course, this comes out of mathematics, but this is sort of intuitive. And then there's an update of the V, which updates your covariance, which updates your uncertainty. This formula is kind of intuitive as well, because you can see Q appears there. And what does that Q do? So if you look at this Q is here the sort of the covariance of the evolution model. So if this Q is really large, what you think is I am moving in a linear way, but you have a huge uncertainty, right? You don't actually know. I mean, you think that's what I'm doing, but if Q is large, you're essentially telling the model that, well, actually, there's a lot of uncertainty and describe random things, essentially. And that comes and inflates your covariance here, right? So if your Q is large, then what's going to happen is you do prediction, your sort of V tilde will increase by that amount. So you're going to say, okay, this is what I think this person must be going, or the object must be going. But of course, my uncertainty is just slightly larger because, that's what the model does. But the opposite is true as well. Okay, so this is the prediction. And the update is exactly the same, except that now you use, instead of the previous posterior is the prior, now you use the predictive measure. Again, sorry for this pi psi changing. These are the same objects. just look at inside and ignore the letters. That's my advice. This is the predicted measure. Sorry, this must be the filter. So filter here. Sorry, the letters are correct. This is wrong. So this is T. So the filter is given by, so if you have the predicted measure, that's just a Gaussian. To recap. Again, a predicted measure, we got a Gaussian like this, right? If that's a Gaussian, and then you have a linear Gaussian likelihood, as I showed in the model, this is the exact formula. So I'm not repeating the likelihoods again. This is the exact formula I showed you for the static case. It's just an application here, except the prior is not the previous posterior, just it is the predicted measure. So you have mu hats here instead of mu t minus 1. Right. And the code is for that is as simple as that, right? So if you wanted to implement Kalman filter, basically these are the two things you do. And this is the I'm showing the code because the notebook that the link that I showed you, the notebook basically implements these two rules. Right? This is basically the code. It's all clear? Okay. So there's nothing hard about Kalman filtering, as you can see. As the pain is to understand these derivations. Obviously, it's a lot of very painful Gaussian manipulation in order to derive these things. Maybe this is the kind of thing that you do once and then you will do it again. Or if you do theory about these things, you do it all the time, I guess. But this is sort of, when it comes to implementation, it is really as simple as 2 lines for the prediction and then 4 lines for the. And you will see there are like different naming for these quantities here. For example, K is called Kalman gain, and there's like huge literature, of course, in control theory and filtering in general to relate to convergence or the stability to these quantities and so on. But we will not go here. So as far as we are concerned, this is sort of the implementation. Okay, so what's an example? For example, I was talking about an object tracking example. If you want to do like an object tracking kind of application, this is sort of the typical model people use. I mean, what is the intuition behind this model? This is also, there's book of, I think this is the one of the citations book of Simo Sarka. If you want to sort of find more examples, it's really, really nice for these sort of filtering examples. So there is this object tracking model that's quite famous in the literature. So what is the model? The model XX is a 4-dimensional state, because how can you guess that? You can see that A is a 4-dimensional 4x4 matrix. So X is a 4-dimensional object, and this is modeling a 2D object. What does it mean? So 2D object has 2 location coordinates. And what are the other 2? What could be physical velocities? Who said that? So the other 2 are the velocities, right? So you have 2 positions and 2 velocities. And then, of course, this sort of matrix describes the evolution of the system based on the previous position. So it is going to take the previous positions and it's going to multiply the velocities by a certain constant. And of course, what it does intuitively is that it adds some constant times your velocity to your position, right? That's what it does when you do this multiplication. Your new position of X coordinate, let's say X and Y coordinates, would be your old position plus the times the constant. And then the object, these are ensuring that object is slowing down. It could be just 1 and it could be just fine. The object would just go on forever in the space. And this uncertainty, the Q matrix, comes from some sort of physical derivation that I will not go into, but this is, there's a relationship between this sort of term here and then how you construct Q. It comes from a continuous time sort of derivation of these sort of models. And most important, the intuitive thing to understand is what H is doing, right? So A is just describing how a 4-dimensional system evolves in 2D. You can imagine, for the people online, I try to use the board as that, like as, I try to not use the board that much, but a drawing would help here. So if you imagine 2D objects moving in space like this, right? So this is xt minus 1 here, and then xt here, and then so on. And of course, it has a velocity dimension, of course, but what you can observe in the object is you can't observe object's velocity, at least the assumption here. I assume that technology is available now, you can observe velocities, but here we don't assume that. We assume we cannot observe the velocity. We can just observe the positions. But we can't just observe the positions directly. Of course, h times x would just give you the first two coordinates, so the locations, plus some noise, right? I can't also observe the locations directly. Obviously, there is some noise. This is as if you're looking from above to this object, you observe its location with some noise around it, right? So for example, this is a very perfect model for something like Kalman filter to be used. I'm not sure if I have, so I can show you. So for example, if you go to this page, this is sort of the implementation. Maybe I can do this. There is the implementation of this. So you generate, of course, in order to do an experiment like this, you first generate data yourself, which is exactly generated from the model. And then this is the sort of system you are dealing with, right? So this black trajectory is the true trajectory we don't observe. The object moves around like this. I don't know which part is the start, to be honest. And then you have these red dots that are your measurements of the object into the. Of course, I'm not plotting the velocity dimensions of the object, right? I'm just plotting first 2 dimensions of the object, but object is 4-dimensional because it has velocity vectors that you also try to estimate when you try to predict and estimate the signal. But we only get these red dots as the data, right? And then if you just implement, because now at this point we know A, so here is of course one of the crucial details. I just gave you A, kappa, and Q, and R, everything you know, right? So here the problem is very easy to solve because we know all these things. Of course, as soon as you go to real world and do anything, you will have to learn these things, which is typically very hard, right? But in the case that you know pretty well what the system is doing, then you can just run this Kalman filter, and Kalman filter reconstruct you the trajectory. So for example, here, probably this was where I initialized it. So I initialized it, it's quite off, but it immediately converged because data is around here. And then you can see, you can roughly see that Kalman filter is this blue curve. I don't know how the colors are visible from where you are, but black curve is matching with the blue curve. Of course, Kalman filter is not overfitting the data, as you can see. It's just try to estimate the underlying smooth trajectory. Okay, so today, if you want to sort of practice or run the code for the first time, if you never have run a Kalman filter, you can just sort of run the thing. It's coded in a very primitive way. If you're a good coder, it's coded in the most primitive way you can imagine, but you know, it's a start. Okay. I just want to introduce another thing in case somebody else or I, if I'm really fast, I don't know if I'm really fast, I don't have the sense of time, but another object that will be very crucial for parameter estimation. So I kept talking that you know your A and H and Q and R, and so you can do all these great filtering things. But of course, you don't have, if you don't have them, and if you want to estimate them, there's another crucial quantity, and I will not show right now why this is crucial. You typically maximize the likelihood why it's crucial. But so this is the likelihood of data. But typically you need to estimate these sort of quantities in order to, of course, build parameter estimation methods, or essentially you can do, this is called model evidence in Bayesian computation. And those of you who like Bayesian stuff would know this quantity really well. This is the quantity that's used to rank models in Bayesian stats, right? So if you have 2 different, let's say, why could you use this? Another use of this thing is if you have 2 different state space models, but a fixed sequence of data. So you have 2 different competing A's, you think they both make sense. You can, for both models, you can compute this and you can look which one is higher, right? If model 1 is higher than model 2, then you can with some confidence say that this model is better than the other. And the nice thing about the Kalman filter is this is also computable in closed form. Like it's no surprise, but it is possible. So how do you do that? So this is the expression. So what is the marginal likelihood? Model evidence, marginal likelihood, likelihood of data, all these the synonymous terms. It's just an integral over all the x's. I guess I forgot x0 as well, or x1, depends on how you construct your model. So you just integrate out all the latent variables. You end up with a function of the data points. So when you see a quantity like this in Bayesian literature or filtering literature, you should think about it as a number. Why you should think about it as a number? It's not a function of y1 to t, which I mean typically written this way. But remember, y1 to t, we assume they are fixed set of observations, right? They are data. They are already observed. And P of y1 to t is an evaluation of this y1 to t as like fixed numbers here. Imagine that there's just numbers. Then this whole thing is itself is a number, right? So the marginal likelihood is also called normalizing constant for that reason. It's normalizing constant of the whole posterior, obviously. Okay. Kalman filter provides this quantity as a byproduct. How do you do that? You can do this sequentially as well. So you don't have to sort of do a batch processing and get your marginal likelihood. What you do is you sort of use this sort of decomposition. And this sort of decomposition basically is true for any set of variables really. And in this case, for y's. And all you need to do is to compute this incremental marginal likelihood or predictive of y, predictive distribution. Again, the language people use vary a lot, but you can recognize by just like seeing it is the prediction of the observation given the past observations, right? And how can you compute this quantity? This quantity is just an integral. If you look at just the last one, given all the yk minus 1, you can construct it this way. If you had the predictive distribution of xk, again, we denoted this sometimes xi and so on, but if you look at inside, you see xk given y1 to k minus 1, and put your likelihood here. Again, g is the letter we used, but p, g doesn't matter, it's the likelihood. If you just integrate out xk, given the likelihood and the predictive measure, you can get this density, right? And is this possible, do you think? Or why is this possible? I have to stop. Yeah.
Because we're nice and linear everywhere. So we
Yeah.
can get the observation model from our signal model.
Yeah, exactly. So this is a Gaussian, and this is a linear map of something. So there is no weird thing in it. And then this is a Gaussian and linear Gaussian. And if you integrate, if you marginalize, I guess these are facts that you can just learn once and use it. Obviously, if you just know the facts, it's very useful, right? You don't need to know the proof. For example, this sort of integral in the Gaussian world is easy. It's possible, not easy. It's easy, I guess. It's trivial from a linear algebra perspective. It's just tedious to derive. You can just marginalize the variables. If these densities are Gaussian and there is no weird nonlinearity in them, you can just marginalize one of the variables. In this case, it's xk. So you can get an analytic retractable distribution, which is another Gaussian. Not very surprising, right? So for example, then you can derive basically the marginal likelihood given in this way. So what is this? This is the predictive. So remember the predictive measure had a mean that was mu tilde, and then v tilde as the covariance. These are those ones. Essentially, you get, of course, the probability of yk given all the data. It's the observation operator applied to the previous mean, the predictive mean, and then the covariance comes out in a particular way, right? If you go into these formulas and play with them a lot, it starts looking sort of familiar, right? And you understand kind of each term better. Obviously, just from one presentation, it's impossible, but if you were to play with these formulas, these make a lot of sense. Right, and what is the importance of this? So Kalman filter gives this as a byproduct. You don't have to do anything. You have to compute it. You have one more line. Typically what we do is we obviously don't compute densities. We never do that. We just compute the log of this. So log likelihood you can compute. Log of this, obviously, log of a Gaussian is just a quadratic. So you keep computing some quadratic. What you do over time, because you have this formula, of course, log of this is sum of log of those other things, right? And every time you compute that, you store it, and in the next iteration, you keep adding. So you do a running sum over time. And this way, you can just get, as just running the filter, you can also get the marginal likelihood for free. Okay. And before I go to more nonlinear case, just motivation. So why this is important? Because people, and I'm guessing that maybe someone, there's particle MCMC course, at least I know that is going to somewhat using it. People usually use this distribution. So the marginal likelihood with the parameter in it. So of course, if you want to estimate parameters given a sequence of data points, and parameters could be A in the linear case, H, other things. In the nonlinear case, of course, it can be anything in the model. You want to typically do, if you want to do an MLE sort of approach, you want to maximize the likelihood. You have to maximize this sort of marginal likelihood, because we are not in a fully observed setting. You can't just directly do maximum likelihood because there are latent variables. You have to integrate them out. So this is that formula. And if you can compute this for any theta, then you can do gradient descent, for example, right? Grad log of this, you can do gradient descent on this, or you can do any other sort of optimization scheme you'd like. So this sort of stuff is very crucial, and it is very good that Kalman filter is exactly possible to implement, to give this quantity to you, because then you can use it to actually learn your A and H and all that other stuff from data. Victor has very interesting work. Okay. Right, so any questions about Kalman filtering? Very basic. I hope most of you didn't know. Not good to hope that someone doesn't know something, but I hope it wasn't too basic. Let's do like a slightly nonlinear extension, right? So we did the linear extension as well. I will not actually show you algorithms, but I will just point you towards the literature, which look very similar to what I showed, but similar in principle. So extend the Kalman filter, I will discuss slightly, but then there is unscented Kalman filter and sample Kalman filter. That's why I call it Kalman filter. There's a lot of Kalman style filters. So most generally, maybe the linear Gaussian model is very restrictive, obviously, for many applications. But this sort of model has a lot of applications, obviously, because only sort of annoying thing could be maybe the Gaussian noise, because you may think Gaussian noise may not be very realistic to model certain things. But as long as Gaussianity is satisfied, you may have this little nonlinear system, right? So what is the difference compared to before? Instead of capital A matrix, we have this A function that could be any nonlinear function. Obviously, for stability, probably there are a lot of restrictions on it, but let's say a stable nonlinear system. And then you can have any H that is also, again, makes the whole system detectable or observable. If your H is completely crazy and crushes all the information, obviously you can't recover X. So you need to place conditions on H in general for system to be detectable in the first place. But as long as that condition is satisfied, then you can have a nonlinear H. Nonlinear H is a very good example of this base station example I was giving you, right? Typically, the signal until it reaches the base station is a very nonlinear process in between, and it depends on the conductivity of the weather and all that, like different things. And people write down the formula of those sort of sensor measurements, right? The sensor measurement, essentially. And engineering literature, electrical engineering literature in particular, has a big number of different likelihood models for different problems. And then, of course, A is a completely different problem to model. H is a bit more like tractable, I'd say, because you know your sensor, you know your conditions, pretty much how you observe the underlying system. But the evolution model is something much harder to sort of write down and get it right. So, okay, for example, one thing to do, so we can use extended Kalman filter or the unscented Kalman filter. These are or the ensemble, I will mention in a bit. These are the words you will keep hearing if you want to implement any of these models. So we can look at one example. This is the extended Kalman filter. So for example, one example is just using simple linearization ideas, right? I mean, instead of using AT xt minus 1, I can linearize AT and HT, right, using a first order approximation. This is anyone who's doing calculus, I guess, would just guess that. You can do Taylor approximation, use just first order approximation to AT. And you can, once you do the first order approximation to AT, you will get a linear system, right? Because it's going to become a linear map of XT. Then you can use the Kalman filter. And that's extended Kalman filter. That's nothing but extended Kalman filter. So what's the idea? Let's say everything will become approximate. Obviously now the posterior, as I show it, like if this is, for example, xt minus 1 given 1, y1 to t minus 1. So this is the posterior of previous time. I usually skip data in order to avoid a lot of repetition. But if this is the posterior, now I have this E here instead of not having E here. Just denote that it's an approximation now, right? Nothing is exact anymore because I linearize my system and I do inference based on this linear approximation to my densities. And obviously at that point, I can't claim that this is the true posterior. right? This is not going to be a true posterior, but it's an approximation of posterior. Okay, how can you do this? You just get, okay, if I am at time t minus 1, again, I am trying to build one-step update, because if I can build one-step update, I can start from time 0. I know my mu0 and v0. I can iteratively apply this, right? So let's say I'm at this point, and I want to do one-step update, meaning that I am at this point. This is the posterior of xt minus 1 given y1 to t minus 1. I want to update to xt given y1 to one step of the prediction and updates. And just the idea here is you linearize your function. So how do you linearize? This is sort of first order approximation to AT, I guess. Linearize around the previous mean, right? That makes sense because you have to linearize your system. You're at t minus 1. This is sort of first order Taylor approximation. So this is the first term. And that AT now is not the same AT as we had before. Obviously, it is sort of the derivative or the Jacobian of the nonlinear map you have evaluated at mu t minus 1, and then xt minus mu t. So this is just the first order Taylor approximation. And you can see now the approximate model, a bar I denoted here, is linear in X. Right? It's just a linear model for us now. There is some extra terms, but they don't matter. So what matters is this linear index. Okay, so if you sort of plug this into Kalman filter, you get sort of a very intuitive update rule of your predictive mean. Obviously, if you're at mu t minus 1, you want to predict where the system is going, and you know the system is evolving with AT. Your best guess of mu t is AT, just classic to your non-linear map, right? And the covariance is very similar to Kalman. Only thing changes is that instead of course, we can't put here the nonlinear map. The problem is obviously the nonlinear transform of a Gaussian is not a Gaussian anymore, right? And that's the entire problem. If you want to do like a Kalman filtering under a nonlinear setting, the question is that I have a nonlinear map of a Gaussian. How can I get another Gaussian? Can I approximate it as another Gaussian so that I can keep doing this, right? That's the entire problem. One approach is this linearization. So I did Taylor approximation to A. If I did the Taylor approximation to A, I get a linear model effectively, and then I get my covariance update as in the linear case. But this AT is obviously the Jacobian now, it's not my Jacobian evaluated at mu t minus 1. And the same is true for the observation model, entirely the same idea. Obviously, now you can see that you can do, you can have a linear model and nonlinear observation model. You can do one of these, right? You have a maybe linear observation model, which is sensible in some applications, but you may have a nonlinearly evolving system. So you can just apply obviously your linearization trick in one of these steps. If you don't need the other, you just use the regular Kalman, right? So for the observation, you do the same trick. You get your H bar as linear approximation to H at the predicted point, which also makes sense because I now built the predicted point. I mean, I have to choose a point to approximate. It makes sense that this is the most recent guess of my state, which is the predictive point. Remember, this is just the AT times the mu t minus 1, I guess. It is the same story. You end up like very similar expression where now you have a linear system with respect to X. So it's linear operator of X. And then this H is obviously the Jacobian instead of again, because we don't have a linear matrix. And once you do that, you remember this massive formula, you just plug that in. Right. So this is the update rule of the Kalman filter as we showed. Again, I just like to write it in one go because it's easier to then sort of show it to you that this is, if you implement it, it is as short as 2 lines if you don't want to implement these things separately. And it is sort of, in this case, you sort of take that rule and then since you're now new linear model, you plug that in here. Right, so there are 4 update rules, again, as in the Kalman filter. Right, so you have these 2 prediction steps, which is basically the evolution of the nonlinear system and the evolution of my covariance with the linearized AT, and your base updates here with again the here's the linearized matrices. So these are sort of the Jacobians, and then actually the observation operator popped up over there. This is the extended common.
I got a question.
How do you know how much error you've introduced in your
Very good question. Yeah, knows. It is very tricky. I think if your dynamics, and if I'm not mistaken, I read a bit of your paper. If your dynamics is contractive, so it's nice dynamics, because I mean, if your dynamics is critically damped, I think it's very hard. If your dynamics is over damped, so it converges to somewhere, then I think you can do something. But
It tracks,
yes,
you can show it tracks the filter, but it's not optimal and you don't know the link with the optimal filter.
so the distance to optimal filter is.
Yeah, it's not an observer. Yeah. We create a control to track the signal, but it's not the optimal filter.
Yeah, so I think I didn't do a lot of work on quantifying errors of nonlinear filters in this form. Yeah.
I just have a question. Since I'm not very familiar with the extended KF. So like at the first time step, you would use the mean of the prior, you would linearize like the mean of the prior.
Yeah.
And then you keep linearizing around the mean of your previous approximation.
Yes. So either the predictive mean or the previous posterior mean. Yeah.
People try to like say at each iteration find the mean or the mode, like because for me it would have been more natural to think of the mode.
Yeah, but I guess if you have a Gaussian approximation, it's the same, right?
Yeah, if you but I would think that you try to use the log PDF of the normalized posterior to find the mode of the actual target, and then linearize there.
I mean, you can.
Because
So you use the non-Gaussian posterior, so you try to find, you try
I would
to
guess that then it feels that it would be quite sensible to the first, like to the initialization, basically, because
yeah, I guess. I mean, it is an algorithm for the online people. I mean, the suggestion is you could. I don't know how microphone picks up.
I think it picks everything. Yeah.
Okay, good then. So you all heard the question. I mean, it's an algorithm. I don't know. I don't know if there is an example of that kind of thing. I mean, it makes sense. You can do a bit of optimization in between. I guess you have to do a bit of optimization in order to find a good point to linearize. You can try. You have to. Well, I have the implementation of Kalman filter, but now you know you can. You can try. Right. So this is one approximation, right? Now I will not go into. I mean, I guess like maybe if we have extra time, we can go into a bit of these things in the second session towards the end, because I may run out of material. But anyway, so here, uncentered Kalman filter is a different approach. So there are all these Kalman filters that people really like and use. And uncentered Kalman filter is one of those. You will hear a lot again if you started to look at these things to apply it to anything. And it actually uses a very cool idea, uncentered transform, which is a more general idea than just to be used in a Kalman filter. So instead of, how we did manage in the previous case, in the extended case, as I told you, the entire problem of doing Kalman filtering in a nonlinear case is we don't know how Gaussians transform under nonlinearities, right? We actually, I guess there's other stuff that is known, but usually in general, we don't. Now, one idea is to linearize around the point and then treat it as a linear map. The other idea is this uncentered transform. So what you do is you take let's say you are at a Gaussian posterior. Instead of linearizing around the mean and then taking a linear approximation to the predictive, what you could do is you could place points in the space and endpoints. I mean, this is going to connect to a bit particle filtering, I guess, because there are different sigma points and particles and so on. But you can place endpoints with respect to your Gaussian, and there's a formula for that. And I'm not showing you the formula, but there is a formula if you go to Wikipedia. The formulas don't make sense if you just look at them anyway. So you place a set of points, and instead of course, linearizing and so on, you transform this set of points using your nonlinear transform, right? So instead of, again, linearizing, you just place a set of points according to your Gaussian. You take a transform of these, that's a nonlinear transform AT, and then you have a set of samples that are now transformed samples. And there is another formula, again, and these formulas are coming from various rules, to reconstruct another Gaussian at that point from those samples. Right, that is the whole idea. So instead of linearizing, you place a set of points, you transform them, and you collect them to another Gaussian. So what you have is you essentially bypass the linearization with another sort of idea where you just transform a bunch of samples to another bunch of samples, and then you get the mean and covariance out of them. Of course, once you get the mean and covariance out of them, you are again in a nice Gaussian world because you approximate predictive with a Gaussian, and you can do your updates. And for the update, it's the same idea. If your H is non-linear, you can again place a set of points, you do the transform, and then you collect them to another Gaussian. So you keep coming back to a Gaussian. That's the important bit, because then the next rule uses that Gaussian expression to place points, right? Because the entire point is to be able to place points in a consistent way. So this is the general unscented Kalman filter idea, and I will not write formulas and go into it, but that's one thing. There's many algorithms, and Gaussian sum filter is one of those. It's just using Gaussian mixture approximations and trying to update these mixtures sort of accordingly. And the most sort of popular one, I guess, and especially popular in weather dynamics and a lot of like very high dimensional problems. And there's a big sort of discussion between, I guess, in the community between particle filtering people and ensemble Kalman filtering people, because everyone thinks that their approach is superior. The ensemble Kalman filter is sort of one of the most popular ones. What you do there is you sort of build Monte Carlo approximations to posterior distribution, right? The entire sort of problem in the high dimensional systems is that you have to store huge covariance matrices. Obviously, when I showed you updates, there's a mean update and there's a covariance update. And if those systems, imagine a weather dynamic system, so it is basically a very large system. So when you see those clouds, all the simulations, it's essentially a 2D grid. And those grids could be like 100,000 points or even more, depending on your resolution. And then imagine that you have to evolve, of course, in order to predict the next day's weather or anything like this, you have to evolve these sort of systems. And of course, mean evolution is sort of expensive but possible, but estimating the covariance or storing a covariance all the time is impossible. So ensemble Kalman filter has this sample-based approach. Instead of sort of updating the covariance, you sort of do Monte Carlo sampling in the prediction, which we will talk about in a bit. And then anytime you need a covariance, you can sort of construct them from your samples, right? So it's sort of an ensemble. You run basically an ensemble of samples in order to get your mean and the covariance. And some of the computations in this way actually turns out to be not as expensive as it would if you do the pedestrian way, which is constructing everything at once. Okay, so this is the Kalman world. There are a lot of very popular variants. One of the and just to conclude here, like slowly, I guess, before I move on to Monte Carlo, there are very interesting recent sort of uses of this sort of ideas. One of it is probabilistic numerics. If you have heard about probabilistic numerics, I don't know how many of you have heard. No one. I'm not doing probabilistic numerics. I'm not offended, but so yes, one of the very nice applications is people try to do. One of the very recent applications I have seen, like Kalman filtering, constantly pop up, and it's new. It's not like classical tracking or classical applications we all know, I guess, or all these. If you go to these fields, these are bread and butter, right? So everybody knows in robotics, navigation, guidance, aerospace, vision, computer vision, a lot of people know these ideas, like it's their bread and butter. But one of the new ones I've seen, as I said, probabilistic numerics, where people try to sort of model numerical errors arising in numerical solvers, as they try to model it as some sort of in a probabilistic framework. And essentially, there's a very tight link between Kalman filters and some of the ODE solvers, it turns out. The classical ODE solvers, you can understand them as, you can phrase them as if they are doing Kalman filtering. So they are implicitly assuming some sort of Gaussian error in the observations. At least that's my rough understanding. Fair question. Yeah, so one of the, and then yeah, a lot of these rules, of course, once you know them, they are very easy to apply. Unset the Kalman filter, unset the transform in particular, we used in a number of applications in generative modeling and so on. Once you know these general tricks, you can essentially do a lot of things. So I would encourage you to sort of build on this introduction, I would say. Okay, so 20 minutes for this session. Right, so great reference in the sense that if I was to write a practical book, I thought about writing a tutorial, and then I was reminded of this book, and then there was no point, right? So this is all the filters here I mentioned are introduced with great clarity here. So it's just like, I think it was lecture notes turned into the book, and everything is as complex as it needs to be if you just want to implement things. Obviously, if you want to understand the theory, this book doesn't have those, but that's not right. Okay, so let's start a bit the Monte Carlo, I guess, before I go into the next session in 20 minutes. Yeah, we have seen that deterministic approximations are only useful if we can ensure this exact and approximate linearity, Gaussianity. Obviously, if you implement a Kalman filter and your errors are student T distributed, heavy tailed, you have a lot of instability of that. And then there's a lot of big literature for the robust, I guess robust every filter, but Kalman filters in particular. And of course, if you're far from linearity, things could be tricky, right? So for more general cases, you have a lot of options. I'm not going to say just this is the only option, Monte Carlo. But you know, if you want to sort of be very general and model agnostic, then one option to build some sort of Monte Carlo technique. So you do sampling. So what is the difference between Monte Carlo and what we have been doing so far? We tried really hard, not that hard, but people tried really hard with other algorithms I showed to get a analytic approximation to the posterior. Right? We linearized. If you use uncentered transform, you place points, you transform your points, you get another Gaussian. So you always want some sort of closed form expression where you know your density and it's typically a Gaussian. But in the Monte Carlo approach, of course, we will leave this. We will forget about having sort of a closed form expression, but we will only be content with sampling. So instead of having a closed form expression of pi of xt given y1 to t, we will just have n samples from this distribution. So we will build or aim at building n samples. And we will try to do the things that we want to do with those samples. So if you want to compute the mean, you're going to average your samples. If you want to compute other moments, you're going to use those samples to sort of build your moments, right? Or expectations. So this is the next goal. Can you build a general Monte Carlo approach to estimate expectations, right? That is sort of, I assume you're going to hear all about this, a general approach or more general approach or more general approach. Okay, so what is the Monte Carlo approximation? So in case, you know, it's good to start from the very basic, then complicate it all the way up to filtering. I guess we can start from something as simple as just plain Monte Carlo. What is plain Monte Carlo? And what do I mean when I say I'm going to approximate the filtering distribution with Monte Carlo? What do I mean by that? It's simply this. So if you have just a target, so forget about now t, time t, and everything. It's just a fixed static target. And of course, Monte Carlo approximation is basically, it basically means if we have access to samples, IID samples from this density, then we can approximate expectations, right? So Monte Carlo approximations typically go hand in hand with this sort of expectation computation. So this is going to be the notation of the integral. You can think about it as like an inner product maybe. So this is an integral of phi against pi. And let's say I want to compute this integral. And obviously it is not a given, by the way, that you can compute for any phi, even if you know this is a Gaussian, right? So this is another problem I didn't sort of go into. Even if you have your density as a Gaussian, you know, any phi you can't compute. You can compute mean and the covariance, obviously, or indicator functions, for example, is not that trivial. But anyway, so we want to compute an expectation. And initially I was talking about these integrals. I told you some examples. Indicator would be here a probability of a set. By x equals x would be mean and so on. And if you have IID samples from it, then the approximation is this way, right? So this is the Monte Carlo approximation on the right-hand side. This is the Monte Carlo estimator of this integral on the left. So you get your samples and average over them and evaluate them at the test function. And phi is typically called test function, and I will probably call it test function. Okay, how does it work? Very simply, if you have never seen this, this is basically, you get this measure, pi x dx. This is a probability measure. and you approximate this with this empirical measure. This is why this approximation pops out. So instead of this, you get your samples and you basically do your best, you give them each equal weights and then build these Diracs. So this is your approximation. I would say, I guess, maybe very poor approximation in some sense to your measure. And once you plug this approximation into this integral, this formula pops out, right? And why does it work that way? There is this, Dirac, because Dirac measure works this way. So if you integrate against the Dirac measure, what it does is it evaluates the function. Right? Dirac, you can think of it's a 1 at one point. So Dirac is 1 at y. Let's say, electrical engineers learn it this way. I guess it's wrong mathematically, but you can say like it's the 1 at y, so located at y, and 0 everywhere. So if you, of course, integrate a function against that, you're just going to evaluate the functions. Avoided mathematicians' anger, but yes. Okay, what is good about Monte Carlo is just this sort of, I guess, like there's a lot of good things about it. It works and so on. And then this is one of the very general ideas we have in general in computation statistics. Obviously, the whole computation statistics based on these sort of ideas. But there are also theoretical guarantees that are nice, right? So one of the very classical results is you can. So this is the estimator I showed you, right? So so this pi n was the Diracs I showed you, and I showed you that if you integrate phi against that 1 over n and Diracs, you would get your 1 over n and estimator. I can write that, I guess, instead of speaking about this. So this is the Monte Carlo estimator I wrote originally, right? So this is just the samples and phi x. Okay. So what is this bound showing you? Bound shows you that the error between your original integral you wanted to estimate and the Monte Carlo estimator in L2 norm. Of course, this is a random quantity. Why is a random quantity? Because these samples are coming from the prior. But target. Of course, you have to take some sort of expectation, and L2 norm is just the squared. L2 norm is just getting complex using. It is just the expectation of the quantity squared and then square root, right? So if you take the square of this would be the squared expectation of this, right? So square this quantity, these are numbers, both of them numbers, square this quantity and take expectation, then you would get like 1 over n kind of rate. Like it's good. Anyway, so the rate is for a bounded function, and I will do very simple. I will always show you the simplest and I guess no very interesting cases, because as you see, the bounded function, assuming that phi is bounded, it works for probability. So if your phi is an indicator, then it works. But if you want to estimate the mean, obviously this theorem will not apply. For the basic Monte Carlo, you can still prove things about the mean for the basic one, but for the open, like unbounded general functions, as far as I know, it's still hard, right? So we will always be in the case of these bounded functions and so on, because I will try to, if I have time again, I will try to do the proofs of these things. So if anyone wants to go in more like in theory, you can at least see the basic proofs, right? And if you want to remove the boundedness assumption in general. Okay, so you have 1 over square root of n rate. And this is a very general rate. You will see it everywhere when you read papers. And people, when they want to say good things about their algorithms, I guess they try to prove a rate like this, because it is the most basic Monte Carlo estimator has this rate. And if you can prove your more complicated, not IID algorithm, so this is obviously IID samples from pi, and then you have this rate. And if your algorithm sort of satisfies this sort of rate in general, then you can argue that it is a good Monte Carlo estimator. I guess it's a good sign that you have an optimal rate of square root of n. Right? Okay, so obviously this is a very ideal scenario. It assumes that we have IID samples from pi, and then you can sort of have a nice approximation. As n goes to infinity, obviously you have convergence of this, and then of course you can prove this for any p norm. So instead of 2 norm here, you can do more complicated LP norm proof. The interest in that is not just theoretical. Like LP norms actually allow you to prove also strong law of large numbers, right? So this is not enough for that, but you can, if you do LP norm, then you can also prove strong law of large numbers that your Monte Carlo estimates will converge. Okay, typically we don't have access to IID samples from pi, right? So I'll probably have to recap this when we start again. I guess I can get questions here because I don't want to go into something complex, just we have 10 minutes. Because then I will not be able to finish just in 10 minutes. I guess this everyone knew. Yeah. Okay. Is it safe to assume that? Okay, so what we will do, so remember now, we wanted to do sort of Monte Carlo approach to the general sampling of the posterior, right? And there are different things you can do. I guess importance sampling is one of the general methodologies that is available in general in the sampling domain. The other one is MCMC, right? You can think about, but MCMC is very ill-suited to this sort of problem because we want to do things sequentially. Right? If you wanted to do something like an MCMC for filtering, there is a lot of approaches related to that, but then you have to run your samplers at every time, multiple times, and so on. And I mean, maybe it may work better, maybe maybe it's not going to work better. So what we will do is we will build on importance sampling. Right. So this is another approach, right? And what is importance sampling? So it's really sort of a simple, based on a simple trick. I guess I can introduce this and take a break. So it's a very simple trick to do importance sampling, right? So, but you need to choose something that's called a proposal. So Q, we will call a proposal. It's not written in the slide, but that's what we will call it. And proposal has to satisfy, obviously, has to be absolutely continuous, or pi has to be absolutely continuous. And then you sort of can write, I mean, this is sort of the fancy measure theoretic notation, and it is necessary for some reason. But if you look at this line first, it is just doing, of course, we assume absolute continuity for this ratio to be sort of well-defined or exist in this case. You take this integral that we originally want to estimate, you just multiply it and divide it by Q. Right? That's as simple as identity trick, you can call it. Okay, what is the nice thing about this trick? This trick is that once you do that, you know how to sample from Q. And if you know pi, and that's another thing we will come to, but if you know pi pointwise, then you can just estimate this expectation, right? You can estimate it. Instead of sampling from pi, you can now sample from Q. Now your new test function, that's proper to call it, is not going to be just phi, it's going to be phi times this ratio. Yeah, so super trivial trick here. Adding this Q. This is sort of how you can write as like in measure theory. There was some discussion between me and some colleague that someone said this measure theoretic notation is just fancy. It's not necessary to understand importance sampling, but I think it is, because when you sample from Q, you just replace the empirical measure here and you don't touch here, right? There's a reason that we don't touch here when we sample from Q. We just use this ratio because it's essentially Radon-Nikodym derivative. So this measure theoretic notation is actually useful conceptually, why you just replace the empirical measure. Okay. So given this, what you could do, obviously, you could just sample from Q, and you can approximate your integral this way. So we didn't do anything new. We sampled from Q. So now we are getting into sort of Monte Carlo. So we will have a lot of weight functions and weights and all these notions. So here we will set, we will call this pi over Q always a weight function. And typically W is that Radon-Nikodym derivative I was talking about. Also, it's pi over Q. So it's just pi x over Qx is W of x, right? And obviously, if I sample from Q over there and apply my standard Monte Carlo trick or approximation, that's just phi times pi over Q. So phi times W of x. So this is my Monte Carlo estimator. And usually we like to denote these things as weights. So it's an evaluation of the weight function. All right, and then we will use these facts. It's important that we know it's an evaluation of the weight function. But obviously, usually they come out and they are just written as simply as weights, right? So these are weights you can think about as weights associated with each sample. And then your approximation in the simple case. So I am assuming that you can evaluate pi. That's a big assumption. I am assuming that you can evaluate this function with pi. Of course, you can evaluate that W function. Provided that that is the case, this is the importance sampling estimator. So there is a difference between important sampling estimator and then self-normalized one. Self-normalized one will not assume pi is available to us, which is obviously the case always. But this one is the basic IF estimator, and that is as simple as this. Okay, 5 minutes. Is this estimator unbiased? Who has the slides? Yeah, I will. No, I will. I it's a good point. I just have to time it, I guess. Is this estimator unbiased? I mean, you see how the Monte Carlo estimator was unbiased. Do you agree with that? Do you agree with Monte Carlo estimator was unbiased? Or
You offer a pint?
Sorry?
Yeah.
yes, yes, of course. So Monte Carlo estimator. I think the camera is it gonna switch. Can you guys see me? Wave your hands. I can see. Okay. So if you have the Monte Carlo estimator, normal estimator, right? So this one. I guess before I go to complex proofs, so everybody agrees this is unbiased. Why is it unbiased? Because we take expectation of the one, and then of course expectation will go into the sum. So this expectation is with respect to pi, and I will get 1 over n sum and exactly the integral I want. And then obviously this is unbiased. So that's good. But what about the basic importance sampling one? Wait, just one time. So that's the Monte Carlo estimate. What is the estimator? I guess you don't remember. So imagine here pi over q, right? So if I take expectation, what expectation is expectation with respect to what? That's the first question.
Q.
Q, because you sample from q, right? And then this is pi over q. So expectation moves inside, so it's an integral with respect to q here. Q's cancel, obviously. And then you end up with pi times pi, right? And I mean, this is, I wanted you to imagine first before I show you, I guess. So you exactly do that. And then you take your expectation inside, these q's will cancel because this q and this q cancels here. And you get back your phi times pi integrated against pi. So this is nice, right? So this is an unbiased estimator. And then obviously we like unbiased estimators. Well, of course, we like the ones with the low variance as well, but in general, unbiased is okay. But this is not going to be, I guess I shouldn't spoil it, but obviously this is the case because we allowed us to be able to evaluate pi. That was the whole reason we got a nice estimator, because we already knew how to evaluate the normalized density. Of course, if you have a general target distribution that you want to estimate and sample from, this is not the case. And then we will handle that case, like extend the importance sampling to that case, and we will see whether the estimators stay unbiased or not. I guess we can discuss that in the second hour or second session. All right, I'm right in time. That's good. Now for now.
Okay, we have a coffee, I think, and we resume at past 11.
Yeah.